Hello everyone, welcome to the OneClass channel and good evening. My name is Fejiro, and I'm an Honors Bachelor of Science graduate currently working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some extra homework help or some tutoring, please check out the links in the description below. We're more than willing to help you. Alright, so now with that being said, let's switch over to our first question of the evening. We have question 1 being, does carbon tetrafluoride have a polar bond? So, as the question indicates, yes, we will start this question by first completing its Lewis structure. For that, we would need to actually know, give me a quick second actually here, almost forgot to actually create these tabs so that way we can actually continue on. But as I am creating these tabs, just be wary that we are going to be creating the Lewis structure for carbon tetrachloride. CH4 F tetrafluoride. I think I wrote the wrong thing down. C4 CF4. Sorry about that. CF4 is carbon tetrafluoride. Oh no. Looks like we've lost one of our files that we can use. That's okay. We have these. And sorry, we're just gonna take a quick there we go, that's the last tab we need. And now let's continue on with the question. Carbon tetrafluoride, does it have a polar bond? So let's first draw out, as I said, the little structure. For that we need to know how many electrons we're dealing with. So with carbon, okay, we're always going to be reviewing our electron configuration here, just because that's always a commonly asked question. So carbon starts with helium, okay, and then it moves on to 2s2 2p2. The reason why I'm not going too in depth in this is just because that's not really the focus of this question. We just want to keep getting down our electron configuration for these type of molecules. So fluorine being the ninth element here, it'll just start with helium, but we have 2s2 2p5. The reason why I did this is because this is the other way of seeing the amount of electrons in the valence shell there are. So with this being said, we're dealing with 4 electrons for carbon and 7 electrons. See how I added these numbers together? So the suffix over there, those are what you'd add together. So with that being said, we have 4 fluorines. So it'll be 7 times 4. So in total this will be 28 plus the original 4 from carbon. And so we need 32 electrons in the Lewis dot diagram. So let's start drawing it out. Carbon will be in our middle because that is the only different one. And so we just draw out at least the first bond of each one, and then we add the fluorine on each side. So now we have carbon tetrafluoride. Please don't forget your actual valence electrons. The reason why I know that fluorine has this much is because if you count it, fluorine still needs to, based on the 7, share 6 more, because right now it's only sharing 1. So when you do the 6, it forms a perfect shell like that. Same with this fluorine, same with this fluorine, same with this fluorine over here. And if you actually count them out, you would see that you actually have 32 electrons, because it'd be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So it's perfect. And if you did your electron number as well, you'd also see that carbon is completely satisfied because it typically has 4 in its valence electron. Subtract how many does it have now by itself? 0. How many is it sharing? 8. Because it's sharing divided by 2, and you do indeed get 0. So carbon is completely satisfied. You should always be getting 0 because, as you see here, carbon tetrafluoride is a molecule with no charge. So theoretically, now when we try the fluorine, okay, typically 1,7, it has 6 by itself, okay, and it's sharing 2 of them with that carbon. So 6 plus 1, that's equal 7 as well. So this is perfect. So all these are perfectly balanced out for carbon tetrafluoride. So what does that mean? Now we can actually say what type of shape it is. This is all tying into whether we have a polar bond or not. But we kind of want to see how we're working with in regards to how it's being pulled. So based on this shape, all right, we have 4 things attached to carbon, which I do add in a different color actually. So 4 things attached to the carbon, 2, 3, 4. So it has an electron, not number, it has electron pair geometry number of 4, meaning this will be tetrahedral. And because none of these 4 things attached to it are lone pairs, it's also going to be tetrahedral shape for its molecular geometry. The reason this means actually that carbon is going to be perfectly pulled by each side, perfectly pulled from each side by the fluorines. So we have this and this. Think of it going in and out of the page, but pretty much this is what we have as a bond. It kind of forms a perfect it's hard to explain really. It's kind of forming like a perfect if I were to draw, it's kind of like a little triangle with like a point up here. So it's like that is the kind of the shape it's forming, if that makes sense. This is what they mean by tetrahedral. Yeah, it's a little bit tricky to try to explain in words, but this is kind of like the shape 1, 2, 3, 4. So you see like that, and the carbon is smack dab in the middle of all that. So because they form that shape is in a sense perfectly stable and wants to be pulling equally at each side. So this actually is a non-polar molecule because every fluorine is pulling equally. But that does not answer what type of bond you actually have. We've done all this to give you a picture of the molecule, but when you actually want to deal with the bond itself, you have to look at something else, the electronegativity. The reason why we did this first, because it all ties in together. If you see, sometimes they'll ask you if you have a polar versus non-polar molecule instead of just a bond. So to understand that, you need to both understand how the molecule itself works and the bond itself work. So now we'll address the bond itself. So for that, we need the electronegativity. So fluorine, right, is quite electronegative. It has 3.98 for its electronegativity. That's fluorine. Carbon is a lot less. It has 2.55. So if we were to subtract these together, 3.98 minus 2.55, the difference, okay, which is 1.43, tells us what type of bond it is, whether it's polar or non-polar. So with that being said, the cutoffs, and I'll just say this because there's a little bit more complexity to it, but between 0 and 0.4, that is going to be a non-polar. And between 0.4 to 1.6, this is now a polar bond. And between 2.0 to whatever number you can get, 2.0 and greater. So I'll actually just do this. That'd be easier. Less than 0.4, greater than 2.0. Oops, I think I did that wrong. Yeah, greater than 2.0. Okay. X is less than 0.4. X is greater than 2.0. That's an ionic bond. Now, what's a caveat here? You're probably wondering what happens between 1.6 and 2.0. If it's bonded with a metal, like a metal and a non-metal, even though it's not 2.0, it still counts as an ionic bond. If it's between two nonmetals, it's going to be a polar covalent bond. Okay, so now with that being said, we have a 1.43, and last time I checked, carbon and fluorine are both nonpolar molecules. Whoops, are both nonmetals. Sorry about that. So because they're both nonmetals, this bond right here is going to be a polar covalent bond. So now you see what happened here? We have polar covalent bonds, but because each fluorine is pulling exactly the same on the carbon, it all cancels out to where we end up with a nonpolar molecule. But this question is asking for the bond, so we could have just skipped straight to the electronegativity, but I want to give you a whole full picture of it, because I don't want you to assume where it's like, oh, if it has polar bonds, it means it has it's a polar molecule. That's not always the case, just as this example here. So with that being said, let's check it out. So they show all the CF bonds are polar bonds, perfect, and because fluorine is more electronegative, that is true. But although all the bonds are polar, the molecule is not a polar molecule because all the dipole momentum cancels out. So does it have a CF? Does carbon tetrafluoride have a CF bond? I mean a polar bond? Yes. This is correct. But is it a polar molecule, as it also says there? No. So with that, let's move on to question 2. Now, this question is asking, when water is placed in the burette, it forms a concave meniscus at the surface. In contrast, so let's actually draw this out. So when water is in a burette, it forms a concave meniscus like this. Okay? And when mercury, it forms in a burette. Okay, sorry about the handwriting. It forms a convex meniscus like this. Okay, so that's concave and convex. I'll probably draw that a little bit smaller. So convex like that. All right. Explain the why this phenomenon occurs and why the two liquids give different results. Provide the meniscus shape if the burette is filled with ethylene glycol. Okay. So let's think about this one. What is water constituted of? Water is H2O. Alright, and mercury is just Hg by itself. That's mercury. Now, they're giving us two concrete examples of what happens, but they want us to explain why. That's the key part. So let's think of it this way. If you have something going like this versus that, right? You'd want to say that these parts are attracted, okay, that's the key part, attracted to the material that is inside. Oops, to the material that it's, that is inside. And in this case, it's a burette, okay? So in a burette, it doesn't really tell us what the material is made of, but we do know that because it forms a concave meniscus, that has to be it. And the reason why is because if you think about it this way, right? When you have water pellets by itself, it kind of just forms a little ball like that, depending on what surface it's on, okay? And you notice that, like, especially when you're dealing with, like, at least I've seen in oily surfaces, you notice that the water gets really nice and circular when it's moving. It's like, yeah, I'm not gonna touch that because it's water, and that surface, especially when it's oily, is hydrophobic, aka no, I'm not gonna bother touching this. But in other surfaces, like, you notice, like, whether it's like, if you notice water dripping down from your bottle or something, it usually drips down in this type of shape. Like, you'll see this is a surface for the oily thing, and the water just running off like that, okay? And on your bottle, for example, the water instead, you see that it kind of sticks and it forms like that, which I'm gonna draw a close-up, be like that, okay? And it's kind of just trickling down the side, and it'll leave a little trail as well. Why? Because water likes that surface. That surface, therefore, is hydrophilic, aka water liking. It doesn't mind water. In fact, it will attract water to it. That's why you see, like on your water bottle and stuff, it will slide and trickle like that. So if it forms this shape here, that means that the water and the surface itself, they don't mind interacting with each other. So in summary, what I'm trying to say here is that the reason why it forms a concave meniscus is because there's something in there that they're bonding that allows it to form that. Now let's go further into figuring out what exactly is bonding there to even make it do that shape. All water is, along with the van der Waals forces that are always present, if you notice, H2O is just 2 hydrogen bonds with oxygen, okay? And those are pretty strong bonds. So that's all the type of force they're working with. So the surface has to be something that doesn't mind hydrogen bonds, or specifically like a strong dipole type of bonds to where it can attach to, which are the hydrogen bonds. Hence why as you pour the water, you notice that some particles are kind of sticking to the side because of the fact that these parts are attracting each other. Okay? And now, let's talk about Mercury. Mercury, I wouldn't say is the opposite per se, but Mercury is just the element Mercury by itself. And because it's forming, as they say, a convex meniscus, we can say that actually because there is no real force of attraction between the Mercury and that Buret. Mercury will, just like how the water, when it's on an oily surface, it kind of just forms up a ball to itself. Mercury forms a convex meniscus because it'd rather be with itself than its surroundings. So it literally pile up on itself and like, no, I don't feel like touching the walls, because of the fact that it has, in a sense, even a stronger bond within itself than with its surroundings. So that is why when water is placed in the Buret, it forms concave, but when Mercury is placed in the Buret, it forms convex. Now, why did this we've answered why now, but the second part is predict the meniscus shape if the Buret is filled with ethylene glycol. So as we discussed with water, the key thing is the hydrogen bonds. Does ethylene glycol have any hydrogen bonds? Well, let's find out. We have CH2, so that's that part. And then we have this, which are just the OHs. And this, I believe, is the formula there. This is ethylene glycol, because we have the CH2s in here, okay? And then we have the OH on the side. Bam, these are your hydrogen bonds. So with that being said, I can safely say, because the only thing that made water stick to the sides was the hydrogen bonds, really, ethylene glycol should also stick to the sides. So if you pour ethylene glycol into that container, into that Buret, it should also form that, because just like water, it has hydrogen bonds. So in a sense, the surface of the Buret is also like, you know what, I can interact with you, unlike the Mercury. If somehow you're able to pour like some, I guess, melted silver or something in there, it followed the same trend as Mercury, where it'd be like this. It wouldn't want to interact. So that is the explanation for water versus Mercury and what would happen with ethylene glycol. This is more of a theoretical question, but nonetheless, hopefully this was able to provide some light in how to explain it. So with that being said, we do check this out in terms of the answer. Concave shape is due to interaction between the liquid and the molecules in the container. They actually say what the Buret is most likely composed of. They say silicon dioxide. So silicon dioxide, SiO2, it's kind of like that. But the point being is that these oxygens are polar. Okay, they have electrons outside of them. And also when you look at the electronegativity as well, between silicon, which is over here, 1.9 versus 3.44. If you do the math, you will see that they do form polar bonds. hence why they had that polarity to be attracted to water molecules. Mercury, on the other hand, it doesn't care. It's unfortunately an element, and elements are content to be themselves and want to hang out with themselves. So they'll just form metallic bonds with themselves. And ethylene glycol, as they say, it's capable of bonding with the silicon dioxide because of the hydrogen bonds it contains. It has a polar part as well. In this case, the polar part specifically referring to the hydrogen bonds I mentioned. So because of that, it's also expected to have a concave meniscus shape. So this is correct as well. And now let's move on to question 3. Alright, so what is a compound name for P4S3? Compound name for P4S3. So you're probably maybe pulling your hair out for this because like, what the heck is this? I've never seen this in my life. So let's make this a little bit easier and break it down into its elements. What is P4 and what is S3? Specifically, what is P referring to and what is S referring to? Well, P on your periodic table is referring to phosphorus, and S, sulfur. Okay? So, now, based on your naming rules, what type of compound do we have? This, I know you can't answer, so I'll say it, is a molecular compound. This is not an ionic compound. Why? Because these are two nonmetals bonded with each other. And when there are two nonmetals bonded with each other, you have to specify these not suffix, what are they called again? Subscripts and the other one. Superscripts and subscripts. Yeah, these are subscripts. Yeah. You want to specify the subscripts. You want to, in a sense, quantify how many you have in the name. So how do we do that? 4, okay, is known as tetra. So we have tetra phosphorus, okay, and 3 is also known as tri sulfur. But you're probably wondering, yeah, we've got the answer. Not quite. We still follow the naming rules for when you're naming, I guess, the anion part, where you drop the same ending and you add the IDE. So this right here is the compound name for P4S3, tetraphosphorus trisulfide. I kid you not, that is it. In fact, if I typed in tetraphosphorus trisulfide there, it pops up. I may have searched it beforehand. But here, P4S3. There's also another name, phosphorus sequisulfide, but these are kind of like the other names that unfortunately you just have to memorize because it falls not really a general naming rule. These will be kind of like when we call a good example would be when we call dihydrogen monoxide water, because those are more of its generalized names. Although there's probably better examples, like I think a lot of the alcohols kind of follow that, like maybe not alcohol, because there's methanol, ethanol. I'll think of some examples later. But point being is that phosphorus sequisulfide is kind of like just something that you'd have to memorize, which wouldn't really apply here because what they're looking for here is if you know how to name molecular compounds, which is why I highlighted tetraphosphorus trisulfide. Okay, so for this they do actually say phosphorus sequisulfide. Technically, as we said, it's not wrong. Yeah, it's not wrong, but it doesn't really help you familiarize yourself with how to name molecular compounds, which is the goal here, I believe. So, for example, if we had this P4S10, this would be tetraphosphorus decasulfide. And if I search that up, which I can, which I will, we should actually get that. Tetraphosphorus because deca is 10, and there. You search it up, pops up, and this one says phosphorus pentasulfide, which isn't technically right. P2S5. We did just double it, but if I did this, tetra 4, deca 10, so P4S10. It's also called phosphorus pentasulfide, which I don't really agree with. It should technically be diphosphorus pentasulfide, but you see, sometimes even I guess the professionals don't follow their own naming rules. So when in doubt, please just go with the given naming rules, because I'd rather be safely correct than possibly incorrect. Nonetheless, this is correct, at least in regards to just what the other name is. So number 4, we have, does resonance help radical stability? So this is also more of a conceptual question. Does resonance help radical stability? Okay, so in short form, yes. The answer is yes, but in long form, how? Okay, let's think of radical stability. That's a tricky one. I'm trying to think of a good example here where we have, I guess we can do that. When an acid, a carboxylic acid, loses its acid, so it becomes like its the base. There's shoot, I forgot the word, conjugate base. There we go. When it comes to conjugate base, so if we had like this, okay. So this is right now what we have because it lost its acid. Typically it'd be like this. This would be the carboxylic acid, okay? But now it's turned to that because it's lost that H, that proton, which is why it says conjugate base. So if we actually drew out just the Lewis structure, okay, Lewis configuration, specifically for that, actually for everything, we'd have the carbon here attached to the carbons. Well, I'll still keep the bonds actually, so this would be a pseudo-Lewis structure. This carbon here is attached to the hydrogens. We don't really talk about that, that's not important. As I said, we're keeping the bonds, so we have the oxygen with the 2 electrons, and then we have this oxygen here with the 3 electrons, okay? So, with that being said, what happens here is that this electron, or any of them really, are able to move about. And you can actually get this electron to move in here, forcing this electron to be out there, which makes now this oxygen up top the -1. So it can now be, instead of a double bond here, we'd have the single bond with the oxygen, and then this will be its new form. This is a resonance structure of that, okay? And so in a sense, you've given, the goal here of resonance is to give the electrons more space to move around. And that is effectively what we've done here, to where the electrons can kind of shift between them. So instead of it being either of those two, they're just like possible electron configurations, I mean possible resonance structures. We'd actually in total get this, where it looks like that. Okay, and they're just sharing that bond. Okay, so this in a sense counts as 1.5 bonds, and overall it just makes the carbon more stable, because that way there's, I mean not the carbon, the whole molecule more stable, because the electrons aren't locked into place. Having just more place to roam free just increases the stability. Now when it talks about radicals, unfortunately I can't think of an example off the top of my head, but it's thinking of like, let's say we had a lone pair like on nitrogen or something like that, and we had something like this, and also was like a double bond. I'm just thinking in terms of like that. I'm just making this up as I go. But if this lone pair is also able to travel around, you know, like anywhere, like, you know, connecting to other bonds and such, the point being is that resonance will also help that stability, simply because the fact that the electrons are allowed to move, which releases a strain on the molecule, on the element itself. So in this case, whatever it was, let's say it was nitrogen that has that bond, because the electron is allowed to move freely, aka be shared throughout all these, the nitrogen feels less stress in a sense of having unpaired electron just hanging out there, because now it's not really too worried about failing in regards to the octet rule. It's like I kind of there because this one doesn't really stay around, it just moves about. So yes, resonance overall, whether it's with radicals or with these types, resonance does help stability because it gives the electrons there more space to roam around theoretically. Okay. So yep, the presence of the unpaired electron makes it unstable and reactive. The use of resonance structures presents a movement of the unpaired valence electron in the molecules through several different possible Lewis configurations, which is kind of like what we did with the carboxylic acid. So through this unpaired electron is treated as a deequalized electron present in the molecule, which represents its movement around the molecule. In this way, the resonance structure helps a molecule achieve resonance radical stability because the electron is allowed to move within there. Okay, so now with all that being said, I just remembered an example of a molecule that its name differs from its official name. Acetic acid. Okay, that one I believe is known as CH3OH, would technically be methanoic acid if we use the IUPAC naming, but its shorthanded form, the one we know, would be acetic acid. I just want to throw that in there because that was tied into what we were addressing earlier in regards to like the official name versus also name they've coined. What is the role of phosphate buffer system in the body? Oh, this number 4, this number 5. This number 5, okay. Role of phosphate buffer in body. So, this is a very good question. Its role is pretty much to keep the pH at certain levels. Sorry, not question mark. What levels, you're probably asking? Okay, we're actually going to refer to our acids and bases sheet, and we're going to look for phosphate, or phosphoric acid. So this will be the last set of phosphoric acid. We want the first one, H3PO4. There we go. H3PO4. So this is one of them, and the other one, phosphoric acid, which is H2PO4, is there, and phosphoric, the last one where it's now HPO4, okay, that one is also here. So with this, if I remember correctly, the phosphorus that we're dealing in our body is usually between these H2PO4 minus and HPO4 2 minus. Reason why I write that is because if I remember correctly, we want our body to stay around almost a neutral-ish, maybe, around a neutral-ish pH. If you look at H3PO4, okay, to H2PO4 minus, that'd be the transition. This buffer system here, based on this, will be based on the pKa. So you see here, we have H3PO4, its conjugate base is H2PO4, and its pKa, which kind of tells you what pH range it will be when it's a buffer system, is 2.12. And I can tell you, as a matter of fact, if our system was stuck at that, we would die. A lot of the stuff, especially when it comes to our stomach and digestion, we do need a mixture of like acids and bases. That's why, you even have acid reflux when it comes to the stomach, because our esophagus, okay, is lined to where, it's trying to protect us with like mucus. But the point being is, if you have too much acid reflux, aka stuff from the stomach bubbling and spilling back up, it's a much higher concentrated pH, literally burning us. And that's not even that significant. It'd be like around like maybe pH of 5. So you can imagine what this would do. 2.12. Yeah, it would literally burn a hole through our stomach. But H2PO4 to HPO4, that buffer range, okay, if you look at it based on its pKa, we have 7.21. That sounds a lot nicer. So this would be our phosphate buffer system in our body. And just as how the pKa shows, it kind of keeps it at this level. We have, I wish I knew the name off the top of my head. There's phosphoric acid, and then there's dihydrogen phosphate. I do believe that's what it's called. And this would be hydrogen phosphate, if I remember correctly. Don't quote me on that. But yeah, so that's the pH we're kind of looking for. And out of curiosity, the last phosphoric acid, when it gets rid of its last hydrogen to just PO4 3-, that's when we're approaching very dangerous pH levels in the basic side. We have 12.32 about range to 12.66. That's what it's saying. So yeah, no, we do not want this. We don't want it to be acidic. This is kind of like the nice middle ground phosphate buffer in our body. And it's actually pretty easy to make this buffer in real life as well. If you have exactly sodium dihydrogen phosphate, so NaH2PO4, that's how it'll be written, and then you mixed it with moles of sodium hydrogen phosphate, which is NH2HPO4, that would actually create this buffer system here, close to a pH of 7.21. Let me just check. Sodium dihydrogen. Yep. And monosodium phosphate. I don't like that name, but yes, it's still there. NaH2PO4 and sodium hydrogen phosphate. Disodium phosphate. Still don't like that name, but yes, Na2HPO4. Perfect. So, with that being said, dihydrogen phosphate ions, awesome. And hydrogen phosphate ion as an ion acceptor. So exactly, we have our conjugate acid and conjugate base correctly identified to get that pH of around 7.21. And yeah, additional hydroxide is neutralized, so additional base is neutralized by our acid component, and excess acid is neutralized by our basic component. Hence how we're able to kind of keep it at that pH. Okay, and that's also why, like, if you drink like too much of, let's say, like orange juice, for example, it comes to the point where you start feeling sickly because of the fact that, like, that's an overload of acidity, and your body doesn't like that. It can only, I guess, supplement so much of this in terms of phosphate buffer to where it can keep your body around that pH, and you can overdo it, so please don't. So with that being said, exactly, phosphate buffers are widely used, which is, I said, that you can literally make them because they kind of mimic the human body, which is what a lot of researchers want to do. So this is correct. Let's move on to the next question. Question 6. Is condensation endothermic or exothermic? So condensation, exothermic or endothermic? And with this, I say it depends, okay, of what they're referring to. Are they referring to when you have something sitting there and you see water molecules form on it? Or are they referring to when literally condensation, like if you think of it, when clouds form before precipitation, I think that's called condensation, where you have the water molecules gather and turn, like the water vapor gather and turn into water and then fall down for precipitation. Okay, the reason why I say depends is because it's very tricky in terms of what system you're referring to. Let's start with this. If the system you're referring to is the water itself, so water, okay, when you go from a gas to a liquid, which would be condensation, that shows a loss in energy, okay? And when you're losing energy, that means, well, hopefully, you're expelling that energy, which is what exothermic means. Exo is the release of energy. So water going from water vapor to water, okay, to liquid water, this is a loss of energy, and that's why it's exothermic, okay? So that is what I want to say there, because of the fact that if you think about it, usually the shapes are changing because there is a less movement in them between the molecules. The molecules are kind of close together, okay, which is why you get the changes from gas all the way to liquid to solid, because the energy is going down, so the molecules aren't moving so haphazardly. They're a lot more kind of close together, allowing that intermolecular forces to really bond between them, making them more of a solid structure. So that's what they mean by exothermic. If we're saying the system was the bottle in this case, or some container, right, to where you would notice that water molecules, like condensation is happening on it, even like in things like like when your glasses fog up, okay, when you enter trying to make sure I word this right, when you go from like a cold environment to a warm environment and your glasses fog up, okay, all right, what's happening there, all right, is that, to simply put, that object, so if you had like a plate, okay, and then you start seeing water molecules form on it, right, it's because the plate itself is absorbing energy from its surroundings. Because remember how water vapor turns into water is a loss of energy? That energy is going somewhere, okay? It's being absorbed by its surrounding. But in this case, the surrounding would be like my glasses, for example. When there starts condensation, it's because the glasses itself are absorbing energy, okay? And because it's absorbing energy, that water, the water vapor surrounding it starts to condense onto my glasses, because there's that energy difference. Like the water is, in a sense, the vapor in the air is giving the energy to the glasses. The glasses are absorbing it. And in this case, this scenario here, the system, if this was the glasses, okay, so the glasses are now the system instead of the water itself. This is gaining energy, and that would be endothermic, okay? A good way of thinking about it is like when you do your calorimetry type of things, is that you notice is that if the temperature of the water were to increase, that means the system inside the water is exothermic because it's releasing water to its surroundings. And if the water temperature were to drop, that's endothermic because now the system is absorbing energy from its surroundings. It's kind of like that, which is why when they refer to condensation, you have to really understand if they're talking about water being the system or something else being the system that they're referring to. Because when I think of condensation, I was thinking of something like condensation forming like on my glasses, but it could also be referring to condensation like when clouds form and then precipitation occurs. The clouds forming and the precipitation occurs is an example of water losing energy to its surroundings because of the fact that you're getting water vapor and it's turning into water. And that also makes sense because as you go up in the atmosphere, it's colder. That atmosphere is going to be taking energy, absorbing heat from the water. So that's why it goes from water vapor to water. And in some colder places like Canada, for example, it goes further than that to where it starts snowing because the atmosphere up there is just so darn cold, it's going to absorb as much heat as possible. Alright, so that's still going to be exothermic when condensation is referring to the water. When you're not talking to something that's not the water, so aka you see the water losing heat, whatever is there, whether it be the atmosphere, my glasses, your water bottle, those things are endothermic because that's where the energy is being transferred to. Those things are absorbing the energy from the water, hence why you get the condensation on the object itself. So let's continue on. Condensation is a process where the water vapor turns to liquid water. That's true. The water vapor molecules come into contact with cooler molecules, and that's the key there. My glasses, okay, they were cold, from wandering outside, and then when I get into a much warmer place, the glass is going to be absorbing heat from the surroundings, including the water vapor that might touch my glasses in the process, hence why you get the condensation on it. Okay, water vapor changes to liquid when energy is lost. Correct. Water vapor needs a physical site for condensation to occur. So you need a site of condensation, which is glasses, the atmosphere, etc. And then once water vapor comes in contact with it, it can release heat and condense into water. Okay. Enthalpy refers to changes in heat. An exothermic process involves a negative change in enthalpy or a loss of heat or energy. And water vapor condenses into liquid, it loses that energy in the form of heat. Therefore, condensation is an example of exothermic process, but I'll still emphasize it's because it's referring to the water in this case and not the cooler surface that it touched. Okay, so now question 7. Okay, so what we have is how can the pH of citric acid be determined? So pH of citric acid. Alright, so this one is a multi-layered question because as this answer says, citric acid doesn't have a pH. It depends on the concentration of citric acid you have to find the pH. So, with that all being said, how do we go about finding the pH from the concentration? So we refer back to our lovely acids and bases table and we look for citric acid because we need to know whether citric acid is a strong or weak base. And what do I mean by that? Strong bases dissociate completely with water, so the concentration of acid directly correlates with the concentration of your H3O, hydronium ions. For weak bases, that's not the case. There's not complete dissociation. So the concentration of your acid, okay, is always going to be more than the concentration of the hydronium ions present, because of the fact that the acid does not dissociate completely. It wouldn't equal each other. So with all that being said, let's look at the table. Citric acid is down here. 8.4 times 10 to the negative 4. So to get a full dissociation, where you have a 1-to-1 ratio, you need a Ka value that we just read out of 1 or greater. That is definitely less than 1. So this would be a weak, I don't know why I put base. Sorry if that confused anyone. A weak acid. That is what citric acid is. It is not a strong acid. So now that we know it's a weak acid, to find the pH, we need to know the correlation between the pKa and the pH. So pH, okay, is negative logarithmic of hydronium ions. And how do we find the hydronium ions? We have this formula where pKa is equal to the concentration of products over the concentration of reactants. So we have the conjugate base times the hydronium, these are the products, and the reactants is the conjugate acid, HA. In this case, HA is the citric acid concentration. So, sorry, it's not pKa, it's just Ka, because pKa is something completely different. So this is Ka is equal to that. So now we need to first find out this concentration here before we can plug it in to get our pH. So this right here is the grunt of the work. How do we do this part? We can't just look at it and figure it out. We need to use an ICE table to figure out how much is dissociated by exactly. So we have initial, change, and equilibrium. And we have now, well, sorry, I skipped ahead a little bit. Before we get there, the reason why we have this as our equation here is because our formula actually is HA plus H2O, which doesn't count as part of our reactants because that's the solution it's in. That's why everything else is aqueous solution except water is just a liquid, and it turns into A minus, which would be the conjugate base of citric acid, plus H3O, which is also going to be an aqueous solution. That's how we get that. This is what we use to get the Ka. So the ICE table, this now will make a lot more sense. Initial, change, equilibrium. Whatever value we get of this HA, let's say we got a quantity, that's a good value, okay? Usually we start out with that value, and with everything else, we just assume we start with 0, okay? And we don't bother with water, okay? That's why I'm just going to draw a dash there. So, with that being said, the change is going to be reflected by, because we have this formula, okay? Whatever amount of moles or concentration you lose of HA, that's the same amount you're going to gain of these, because it's all a 1-to-1 ratio, okay? So, although it's not fully dissolving like that 1-to-1, where if you had 0.5 of a strong acid, you'd have 0.5 of hydronium, it still transfers 1-to-1. So it'll be minus X plus X plus X, okay? So now we have Q minus X will be the equilibrium, and these will just be X. So if we use back our Ka formula, we have Ka is equal to X squared, because that's what we have in the top, 2 X's, divided by Q minus X. Now here's the part I love explaining. It's kind of well, it is not even kind of, it is a shorthand, but you can only use in specific conditions. If the concentration that you're working with is 1,000, so if Q is 1,000 times bigger, and it's arbitrary, but that's what they chose, 1,000 times Ka, alright, then the change of Q is so insignificant that it actually turns into just being this. Ka is equal to X squared over Q. And you save yourself from having to do a quadratic formula. Because in a sense, what's happening here is that the concentration of Q is so big that even after it dissociates, it wouldn't even impact it to where you have to note it down. Like if I started with 1 moles per liter of that object, the change would be so little that when I round it, you'd still get 1 moles per liter. Hence why we can use this. But on the flip side, unfortunately, if Q was less than 1,000 times Ka, it means that it does dissociate quite a bit, enough to where you have to factor it in, and you end up still with this formula. Ka is equal to X squared minus Q over X. X squared over Q minus X. So to solve for X in the easier one, that's what we're going to start with. We have just Ka times Q, okay? And the square root of it is equal to X. And there. and you pick the positive value because of the fact that x has to be a positive value. You cannot start with 0 and end up with less than 0 when you're working with solutions. So yes, it would just be the square root of Ka times Q. If we had this one we have to deal with, unfortunately, you have to now multiply both sides again. So it'll be Ka times Q minus Ka times x is equal to x squared. You have to rearrange it to where you get x squared plus Ka times x minus Ka times Q is equal to 0. And then to the quadratic equation with 1 being your A, Ka being your B, and Ka times Q being your C. So what you get is that we have negative Ka plus or minus the square root of Ka squared. And in this case it would be plus 4 times 1, which would be just 1, and then times Ka times Q. And the reason why it's plus instead of minus is because if you notice, the Ka times Q, that C value, is negative. And then all of this will be divided by 2. And once again, you choose your positive number of the two. Point being is that overall, both ways will get you your x. So now that's complete. And then your x, based on this, would translate into the amount of hydronium you have. And because you finally found the amount of hydronium, you can now find the pH, which is the easy part, negative log H3O. So yes, this is how you determine the pH of citric acid. Not so easy at first glance, but that is the way you'd have to do it. So lemon juice, it says 50 grams per liter. We can actually test this out. 50 grams citric acid is according to this 192.124 grams per mole. So in this question here, 50 grams divided by 192, we have 50 divided by 200, that's like 0.25 moles per liter, okay? So we have 0.25 moles per liter, and let's just skip over to using the more complicated form because you always want to just be more accurate than inaccurate. So the Ka of citric acid is, where is it? Citric 1. That's what we want to work with. 8.4 times 10 to the negative 4. So we have 8.4 times 10 to the negative 4. And we want to square that because that's what we do. And then we're going to add plus 4 times 8.4 times 10 to the negative 4 times Q, which we had was 0.25 because that was the moles per liter. Okay, and then we square root that. Alright, and then because we want to have the positive number, we're going to keep that positive and add that subtract the Ka, the minus Ka. So it'll be minus 8.4 times 10 to the negative 4. Okay, and then we divide that by 2. We get an x value of 0.014. So of the 0.25, 0.014 dissociated, which is still quite a big amount of it. And then now we use that to find the pH. So negative log of the answer, we get 1.85. So going back to this question, citric acid 50 grams per liter is pH around 2 to 3. We actually found this pH to be 1.85 in this theoretical example. This is technically correct. Actually, this is incorrect. I was going to say it's technically correct because citric acid doesn't have a pH of its own, but in terms of finding the pH, they don't really do a decent job of explaining all the steps you have to do, and it can kind of lead you astray if you don't understand that. So we do that, and now we have this question, another conceptual question. What is the value of activation energy of uncatalyzed? uncatalysed. reaction. Okay, so for this, we're more so thinking in terms of answering this in regards to catalyzed versus uncatalyzed. So what does a catalyst do to an enzyme due to the activation energy? The goal of the catalyst slash enzyme is to decrease the activation energy. There's no real value. Okay, so if I were to draw this, the original activation energy without the catalyst would look like this. Okay, typically. Okay, and this indicates that there's a loss in energy, because at the end, I guess, you release heat, but you first needed to build up all this energy first before you could actually get to the activation energy. But what a catalyst does, it says, you know what, I admire the hard work you do, but we can make this a little bit easier. Whether it's through enzymes or just a constitutional change in the catalyst and whatnot, it allows you to do that. So you still end up with, so I can draw that a little bit better. So you still end up with the same reactant, same product theoretically, but a catalyst just makes it so that it's a lot easier to get to. And whether it involves in terms of changing the intermediate steps and such, the goal is that there's going to be less activation energy when a catalyst is involved. So with that being said, the value of the activation energy of the uncatalyzed reaction, so when the catalyst is not involved, it means that there is catalyst involved. It means that there will be more of an activation energy threshold you have to get to. So that would be how you would answer this question, because there is no value per se, because each reaction has different activation energy. You just know that it would be more than if a catalyst was involved. There would be more energy needed when there's no catalyst involved than when there is a catalyst involved. Okay? So exactly, catalysts are substances that increase the reaction rate of a reaction without being consumed in the process. That's key, because a catalyst is not actually part of the reaction. Well, I phrased that wrong. The catalyst is part of the reaction, but the catalyst stays there. It does not get used up during the reaction. So kind of like if we're dealing with enzymes as an example, the concentration of reactants may be high and the enzymes may get saturated. That's how they keep working. They keep working, breaking down, changing the reactants into their products, and then they say, okay, next one's up. The enzyme itself doesn't dissolve and go away. Technically, that's a whole different conversation, but point being is that the enzymes don't do that unless you had some other things that break enzymes down, which is what your body needs, because sometimes your body wants to stop breaking down certain things, so it deactivates certain enzymes. So all in all, point being is that the enzyme does not get used up by the substance itself. That's a key thing that you want to understand. So catalyst does not appear in the overall stoichiometry. That's true. The catalyzed reaction would therefore have a small activation energy. So from this graph, you can see here, catalyzed reaction, which is correct. It's a loss of activation energy than without a catalyst, as you can see here. Alright, so that is pretty much what a uncatalyzed reaction has, is that relative to the catalyzed reaction, there is more energy needed for it to be activated. So this is correct. And now let's move on to question 9. Depict the electron configuration for phosphorus using an orbital box diagram and noble gas notation. So give one possible set of 4 quantum numbers for each of the electrons beyond those of the preceding noble gas. So let's first do the less fun long-handed version that they asked for. So for phosphorus, it's not too far away, which is good. But if we wanted to get it, it's the 1s, 2s, 2p, 3s, 3p, 3d, okay? And then 4s, 4p, 4d, for F. But for phosphorus, we're kind of only going to, whoops, sorry, I skipped ahead. Definitely didn't even write the question down. Not the best habit. But nonetheless, electron configuration of phosphorus and orbital box notation as well. Okay, and give possible set of 4 quantum numbers. So with all that being said, for those preceding the noble gas, okay, with all that being said, so phosphorus, we can see here that it's the 15th element, okay, so it kind of blasts right through the first shell. So hydrogen is done, and helium, so we have 1s2, and then for the 2s row, it's past lithium and beryllium, so we have 2s2, and then it's past neon, which is now the 2p6, okay, and it blows right past through sodium and magnesium, which means it fills the 3s2 as well, and then it also goes past aluminum and silicon, and then there's phosphorus, so it's right here, so that'd be 3p3. That is what phosphorus ends up as. And if we were to do the noble gas notation of phosphorus, we start with the previous noble gas, which is neon, okay, and then we have 3s2 3p3, okay, and then they're asking for the orbital box notation as well. I'm not going to do the full one because it gets really tiresome. Fine, you've convinced me. So with that, we're gonna actually draw it out, and this is the orbital box notation. Okay, so we have 1s2 because there's 2 electrons there, 2s. Oh, I forgot something. This, but I don't like it. This is the 1s. Actually, I have the ones on the side, so this is the S, this is the P, whoops, rush that one, S, 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 and these are the P rows, and you'll see why, based on the 6, okay, so we have 2S2, 2P6, don't be deceived at how I'm drawing them, they get filled a little bit differently, okay, and then we have 3S2 completed, and then 3P3, and it goes like this, that, and that, because it fills its first electrons in each subshell first, okay, it doesn't kind of bunch it together. So with that being said, the noble gas notation for this, okay, think of it as we start with the 3, we just say that it starts with neon, okay, and then we have our boxes again. Alright, and then shoot, forgot one more box, haha. And then we have the S, that's done. Then we have the 3P3. Okay, so now with that being said, this is our 3S, 3P, 3P, P. So we've successfully drawn every type of form for it, shorthand and the longhand form. So now they're asking us for the possible quantum numbers for it. So as a review, there's 4 quantum numbers, okay, as I mentioned. We have the N, we have the L, ML, and MS, okay? So N tells you what shell we're on, and they specifically ask for the quantum numbers in the valence shell, so past neon, okay? So as you notice here, all we're dealing with, which is N, is 3. The N always has to equal 3, specifically for phosphorus, when it's past its, when it's in its valence shell, because the fact that we've gone past all the other orbitals, the first, second orbital, we've passed through them, and we're on the third orbital. The L, okay, for this one, it'd be easy to break this down this way, okay? So L, when L is 0, that means that we're in the S shell. L is 1, we're in the P shell. L is equal to 2, we're in the D shell. And L is equal to 3, we're in the F. Considering that we're only dealing with S and P's, we're only going to be dealing with zeros and ones. So L can be 0 or 1, okay? ML is a possible, is a positive and negative values of your L. So if you look at your L, okay, we can have either 0, okay, for the 0, and then for the 1, we can either have -1, 0, or 1, okay? These are going to be the different MLs, and you'll notice that it actually match perfectly with your S and the P rows. We have the S for the 0, and the P is -1, 0, and 1, okay? And the MS just tells you what type of spin it has, which is going to be -½ or 1/2, okay? That's the only two choices it can be, all right? So now they just want us to give us, they want us to give just one example of a possible set of quantum numbers, okay? Let's say we chose this one, okay? This one, theoretically, if we're following this, okay, if this was the -1, this was the 0, and this is the 1, okay, this would be 3, 1, okay, 0, because it's in the middle, in the P orbital, and then it can only be 1/2 because only half of them are there. Whoops, sorry. I believe you start with a negative spin. It can only be -½ because each one has a negative spin there. I may be wrong about the spin part. I don't remember which spin you start with. Okay, so you start with a positive spin when it's pointing up, which makes sense because it's pointing up. So it'll be +1/2, okay? And with that being said, then that means anything in your P shell, so anything that has the 1, you would have a +1/2 because that's the only one available. If you're dealing with something in your S shell, it would still be 3, but now this would be 0, and then this would also be 0. There's only one of them, and then you could choose either a +1/2 or a -1/2. A -1/2 in this case will be referring to this one right here. Alright, so these are two possible very real combinations for the electron in phosphorus, okay? So as we see, they got the same answer we did when it comes to right now it's full form. And then we have 3s2, 3p3, perfect. We have this, and they actually were nice enough to list off every single combination. So as you see here, actually, we have 300 +1/2 and 300 -1/2 we did here. Then we have 3-1 +1. Okay. Oh, I get. Oh, interesting. Well, yeah. I guess it doesn't really matter which one, as long as you're keeping track of which one's your positive, which one's negative. But to keep it constant, I'll just follow them. So this will be +1. This is -1. I guess the pluses always come before the minuses. This is a good rule of thumb. So you have 3, 1, 1, +1/2, and 3, 1, 0. So that's what we got here. And then +1/2, and then 3, 1, -1, +1/2 as well. So this is correct. Okay. So that is all you need to know about electric configuration and how to actually go about giving them the quantum numbers. Okay. So now question 10. We want to classify whether each of the following are elements, compounds, or a mixture. Okay. So this is relative. We're going to kind of blaze through this because at first glance, most of these are relatively straightforward. Okay, so let's start with diamond. Okay, diamond is composed of carbon. Okay, only carbon. This right here is considered an element. Okay, and that's all you need to know. Diamond is an element because it's only composed of carbons. Alright, air. Okay, it's a mix, already hint there, of water, nitrogen gas, oxygen gas, like water vapor, whatever's in the atmosphere, whatever's in the air, a lot of different things that you inhale and exhale. Unfortunately, if somebody like farted, methane is mixed in there as well or something. But point being is that it's a lot of different compounds mixed together. So that one would be a mixture. Krypton, as the name shows, is just the element krypton. This also be an element. Alright, water. This would be just a compound and not an element, because as you can see here in its name, it's composed of different things. So water is a compound. And with that note, ammonia is also a compound. And wood. This one is going to be, ooh, that's tricky. That's real tricky. That's real tricky. I'm gonna say it's a mixture. Yeah, because, oh man, how do I even explain this? Mixture of compound. It's definitely not an element, because you can't find wood on the periodic table. I want to say it's a compound, because that's a very specific part of, I guess, trees. If it was like a whole tree, that'd be more of a mixture, because it's made up of different compounds to put together. Like humans, we're mixtures, because we're made up of different compounds. Shoot. But if it's just wood, if we're assuming, nope, because wood cells have different molecules in them, I'm gonna say it's a mixture, because the fact that we're dealing with organic elements, and if like they're, you know, obviously like us, where we have cells and everything, cells are a good example of also mixtures, because not everything in the cell is made up of the same type of compound. You have carboxylic acids, you have hydrocarbons, you have sugars, you have proteins, you have fats, and those are all different compounds. And even those fats, for example, are different types of fats, which are different compounds. So I'd say it's a mixture. And you know, same thing with like plant life. You know, in a plant cell, you have very different types of compounds in there. Dry ice. Okay, this one's a compound because of its formula. Okay, it's just there. Sugar is a compound. Same reason. Sulfuric acid, also a compound. Okay. And bismuth is just, you can actually find it on a periodic table. It's just an element. Okay. Alcohol, you can actually see it. It's going to be a compound. Okay. Salt, still a compound, but it's an ionic compound, but you still say it's a compound. Bronze. Okay. Bronze. Ooh, that's tricky. This is a compound. Okay. And to further elaborate, this is a metallic compound. I'm not sure which metals, but different metals are bonded together to form bronze. Maybe wrong about that one. Baking soda is a compound as well. Milk. Surprise, surprise, is actually a mixture. Because just as how you see the 2% milk, 5% milk, you can tell from the percentage, a lot of it, as the name implies, is actually like water. And then the other is like the actual like lactose compound in there. And that's what constitutes as milk. Gasoline. Oh my gosh, this list is amazing. Is actually a mixture as well. Because if you remember, well, I mean, I'm not sure if anyone has actually gotten gas if you're watching this, but for those that have, you can see like the different levels of gas. Those are like in terms of like its purity of how much of a certain compound it has, where it has like other impure substances in it. So it's actually a mixture as well. Okay, uranium. I'm actually gonna highlight the ones I'm not sure about. Bronze. I think I've convinced myself on wood. Uranium is an element. Okay. Pail of garbage. Okay. It's a mixture. I got stumped because the next question is energy. And energy, I'm gonna just say that it's a none. Because even if you're thinking of like neon lights, you can say that's an element, but energy itself, where you have like electrons moving in and out, or if you have like positron decay or like anything happening where energy is released, that is usually shown in the form of like waveform particles. So if we're dealing with particles, I'm gonna say they're elements. That's the closest thing we can get to. But I'm gonna say that technically the best thing would just be saying none, but I'm gonna say element in this case. Ink is a mixture, because same thing kind of like with the milk. It's water and other things. Titanium is a element, because it's actually shown on the periodic table. Iron is also an element. Electricity, I'm going to say elements as well, kind of following the same as energy. Okay, these two. Okay, when you're transferring electrons and stuff, you're still working with particles. That is what electricity is, the transfer of electrons typically. That's why you have like the voltaic cells and all that stuff. But yeah, popcorn. Following the same trend of wood, I'm going to say it's a mixture, because each cell, because popcorn is technically an organic stuff. It's not living anymore, but you get what I mean, as it has cells in there, and those cells compose of different things. A dog, just like humans, and popcorn, it's also a mixture. Gold is an element. Pizza is a mixture. And concrete is going to be a mixture, because if you ever heard of like concrete mix, and it's like a mixture of just different stuff together, because if it was, that's the thing, like assuming if it was a compound, concrete theoretically would have like the same color, shape, and everything, like all uniform. We notice that there's all these bumps and everything. There's rocks mixed in there as well, literal rocks. Those aren't the same compounds. So with that being said, let's see how we did. Alright, so let's go back to the top. Diamond element, perfect. Air mixture, krypton element, water compound, ammonia compound, wood mixture, nice. Dry ice compound, sugar compound, sulfuric acid compound, bismuth element, alcohol compound, salt compound, bronze mixture. Oh, that's unfortunate. So we are on a roll. But I guess that makes sense because, well, what is bronze a mix of? Let's actually find out. Bronze is made of copper and tin. It's an alloy. Are alloys mixtures? Alloys, all alloys are mixtures, but not all mixtures are alloys. Interesting. So bronze is a mixture because it's an alloy. Good to know for metals in general. So metallic compound, well, they're not even metallic compounds, they're called alloys because they form metallic bonds with each other, like tin and copper. That's what copper and tin to make bronze. So just remember that. Even though they're considered metallic bonds, these are alloys, it seems. Okay, so baking soda, where are we? Compound. So this is the one I'm gonna underline, the one that I think do stand out, like that. Baking soda is a compound. Milk is a mixture. Gasoline is a mixture. Uranium is an element. Pail of garbage is a mixture. Energy, not any of them. Thank you, I had a feeling. Electricity, not any of them either. So yeah. Ink, mixture. Titanium, element. Iron, element. Popcorn, mixture. A dog, mixture. Gold, element. Pizza, mixture. Concrete, mixture. Okay, so we're kind of on the same page for everything, but remember that alloys, which is like bronze, and even a good example of an alloy is also like steel. Steel is an alloy, okay, and steel is a mixture or a compound. You should see that steel is a mixture. Yep, steel is a mixture of iron and carbon fused together. So in fact, it's not even a alloy because it actually has carbon in it, but still a mixture. This is correct. More correct than mine, that's for sure. We gave it our best shot. Let's move on to question 11. So we have what is a Ka of a strong acid like HCl? So if you remember, tricky. The Ka of a strong acid like HCl. So they actually give us a hint in the name right here, strong acid, because we actually don't even need to. We will check our acids and bases sheet, but we actually don't need to. If you're dealing with a strong acid, the Ka is greater than 1 for strong acids. That is what this question is asking. What does that mean in regards to HCl? It means that when HCl reacts with water, it will completely dissociate. Well, this hydrogen will completely get off the chlorine to where you only have these hydroniums relaxing. That's all you'll get. And that means that the Ka value would be greater than 1. We don't know exactly, we just know that it's greater than 1 because of the fact that it's a complete dissociation. Whatever value you have of HCl will be the same exact value you have of Cl and H3O once you're done. You pour some hydrochloric acid into water, completely dissociate, you get these. You start out with 1 mole per liter of hydrochloric acid, bam, you have 1 mole per liter of chlorine ions and 1 mole per liter of hydronium ions. So, with that being said, they actually were able to give a value. If you look at the acids and bases sheet, it just says strong acid Ka greater than 1. To find the Ka value, you really have to just look at the literature, whatever they say, just because it's just kind of like at a point when you go past 1, it doesn't really matter what your value is. It just pretty much signifies that when you're put in water, you're not staying together. That's what it means by complete dissociation. So let's move on to question 12 now. All right. So what we have for question 12 is, what is the difference between a mixture and a compound? We came to rub it in. So, difference between a mixture and compound. Okay. So, what is the difference? So as I say here, because I will read this, compounds are substances that are formed through the formation of chemical bonds. Okay. Mixtures, on the other hand, aren't dealing with bonds. Okay. So to, I guess, write in a way that's a little bit more easier understood, compounds are bound together by bonds, intramolecular forces. Mixtures, on the other hand, are bound together by interactions. Okay, intermolecular forces. Okay, so unfortunately, because we can't see air, that wouldn't be a good example of a mixture that's kind of held together. But let's look at us as humans. Okay, I can see where my hand starts and ends. Okay, hopefully that is because I'm a complex system of mixtures held together by interactions, intermolecular forces. Water, okay, compound, is just H2O throughout, because that is the only, well, I guess to further explain water, H2O, you have a compound there because it's specifically referring to the water molecule. Okay, each water molecule is formed like that. This is all that's there when you talk about the compound water, H2O. Now, even if you have multiple H2O, like when you have a glass of water, that's still just known as a compound, because you're not throwing in any other type of element or molecule in there that would be just interacting with it instead of bounded to it. If I had, for example, a whole bottle of H2O2, hydrogen peroxide, that's just going to be a whole, bottle of that compound. But if I said I'm going to mix that with NaCl, okay, now we have a solution, well, a mixture, okay? It's going to be a salty H2O2, because now we have different types of molecules that are interacting with each other. This is considered a mixture. It's no longer now they're bonded to each other, they're interacting with each other in that solution. Kind of like referring back to humans, we have a lot of fats, carbohydrates, and proteins and amino acids that make us, okay? And all those things are interacting with each other. And even when I list them down, there's different types of fat, different types of proteins, etc., to form the complex structure that is us. And a lot of these things are interacting with each other in our body. We are a mixture. Hence, they even said, like the previous question before, a dog is a mixture. Because the key thing is that a dog, or even us, we're not made completely of the same compounds. There's different compounds in us. And then now flip it over to compounds like water, oxygen, gas. Those things are only composed of those compounds in there. Like oxygen gas only has O2 in it. There's no like nitrogen or something floating in there as well. So that is the difference between compounds and mixture. All right. And typically, that's just it. I'll leave it there. We can delve more on how to separate them and such in other questions, hopefully. Now, question 13. How would you arrange the following bonds in order of increasing ionic character? Okay. arrange in order of increasing ionic character. All right. So for this, what we actually have to do is we have CF, OF, HF, and NAF. Okay. So to figure out the increase in ionic character, we actually deal with just the electronegativity, starting with CF. Okay, remember that question we solved earlier where we figured out whether carbon tetrafluoride. You'll be able to find that in another video, but point being is that we were able to see there that they were polar bonds, but it wasn't a polar molecule. Here we're just going to expand on that. So we have here 3.98 for the electronegativity of fluorine, which is actually what everyone's using here. So we're actually going to list out just the other one instead. So carbon is 2.55. So 3.98 minus 2.55. You want to know the difference. So the difference here is 1.43. Oxygen has an electronegativity of 3.44. We have 0.54. HF, okay, hydrogen has a electronegativity of 2.20, and sodium, just so we can save time a little bit, has 0.93. Okay, so hydrogen and fluorine, we have 3.98 minus 2.20, 1.78. And sodium fluoride 0.93, yeah, 3.05. So to arrange in order of increasing ionic character, we just arrange in order of electronegativity. So we actually have OF less than CF, which is less than HF, which is less than NAF. And we can actually discuss what type of bonds they have. So if you remember our bond range to tell us whether it's nonpolar covalence, okay, it's 0 to 0.4. Polar covalent is 0 to is 0.4 to 1.6. Well, I'll just say it's less than 0.4 to make it easier. And ionic is greater than 2.0. All right. And the range between polar and ionic is that from 1.6 to 2.0, theoretically, is that if non-metal and metal, it's still ionic. Okay. So with that being said, although we have our order, you can see here that oxygen fluorine, this is still going to be a polar bond. Okay. Same with these. But this hydrogen fluorine, it's 1.78. But hydrogen is a nonmetal, and so is fluorine. So this is still just a polar bond, but it's a special type nonetheless. Not because it falls in the range, but if you recognize it, it's actually one of our hydrogen bonds. Okay, because it's attached to a hydrogen with a fluorine. The three types of hydrogen bonds are nitrogen, oxygen, and fluorine. And so that's one of them. NAF, as you can see here, is greatly bigger than 2.0. So this is an ionic bond. And as you remember, hydrogen bonds are stronger than polar bonds, but ionic bonds are stronger than hydrogen bonds. Hence how this range actually makes sense too. So let's see how we did. OF, CF, HF, NAF. Perfect. So CF, OF, H, and NAF. Exactly. So we definitely got that correct, and it gives the highest value. It exhibits the highest ionic character of NAF specifically, followed by HF, because that's a hydrogen bond, which makes sense. Then CF, and then lastly is OF. So this is correct. So now let's solve question 14. How do we convert tablespoons to grams? So this one, tablespoons to grams. Okay. So for this, we actually need to know our conversion sheet, which I had earlier, but unfortunately that's a page that's not loading properly. But the point being is that we can actually set this up properly. So first thing is that we know we start out with tablespoons. So X tablespoons, okay? And then we have certain amount we don't know yet, but we want to be able to get tablespoons crossed out. So we put that in the denominator, and that corresponds to how many grams you have. And once these cancel out, you'll be able to get X times whatever divided by whatever to give you your grams. So now for this, turns out tablespoons is actually a liquid measurement. So you can actually search it up here, although I wouldn't trust this because usually it refers to, like, I guess, water. But if I said tablespoons to grams, okay, it says 21.25 grams, okay? Well, that's like baking conversion table. But this answer here actually brings up a good point, that tablespoons typically are a measure of volume, while grams is a unit of mass. And if we are going based off of that to even get to this point, what they did here is X tablespoons, okay, and we're still canceling out the tablespoons, but now we know that there's 15 milliliters per 1 tablespoon, okay. And now what they've done here is that they say you need the density, and density, okay, is going to be, so density, which is volume, is equal to, I'm trying to remember what density is. Oh yeah, mass over volume. Yeah, that's the density. So with that being said, if we wanted to find now mass, that's a key part, we have mass is equal to volume times density, okay. So then that means we need, whatever we're measuring, we need to know the density of that object, okay. So it would be, I guess, A. Alright, because now we're getting rid of the mill, okay. Volume times density, just make sure we have the correct one. Actually, no, it wouldn't do this. We have 15 mils. Oh yeah, no, this makes sense. Sorry about that. So we have A, and we have A mass, so A grams over, I guess, certain amount of mils. The reason why we put the mils here, grams per 1 mil, because if you see the density written in units, something grams per mil or kilograms per liter, that's how you calculate density. So these two will cancel out. So depending on what your density is, like I can say my density is 0.78 grams per liter. I think that's like the density of like methane or something. But nonetheless, this is what we do here, because now our goal is to get to grams. That's what we've done. Tablespoons are canceled out. So in total, we'd have in this theoretical answer 15 times A times X grams would be how to get to your grams from tablespoons. As you've seen here, we've canceled out every appropriate units and ended up with just grams. So that being said, this is correct. So let's move on to the next question. Question 15. For this question is asking how many quarts are in 1 gallon. Well, the hint is in the name, but we're still going to go through this using the structure we had earlier, but the structure being that we want to make sure that we have what we're starting with, which is quarts. Okay, so that's x quarts times, and based on this conversion, we know that there's 4 quarts in 1 gallon. So based on that, we cancel it out. So whatever quarts you have from this question, okay, your gallon is going to be x over 4 gallons. Whoops, I definitely solved this wrong. Well, I solved this backwards. So what I solved was that if you're given like 20 quarts, you have 5 gallons because we have x over 4. But for quarts in a gallon, we're actually starting out with gallon, okay, because it's saying quarts in a gallon. So you have x gallon, but it still follow, and you'll notice when I actually write it like this, 1 quart, well actually it wouldn't be 1, it'd still be 4 quarts in 1 gallon. The gallon units now this time cancel out because one in the numerator, one's in the denominator, and you still now get 4x quarts for whatever gallon you're given. So if I got 5 gallons, that would be 20 quarts. Okay, so this is correct. Oops. So now let's move on to question 16. What are the intermolecular forces in CHF3 and CHF3 OF2 HF and CF4? So let's actually just write them down like in more of a linear pattern. So, well, actually, let's keep that there. I'm just gonna rewrite it so we can space it out a little bit. CHF3 OF2. Trying to figure out a way to do this. HF and CF4. So the first intermolecular force that's always present in everything, okay? All right. So if we said London dispersion force, that would be all of them, okay? That's the first force that's always found in all of them, okay? Now, the next type of intermolecular force are dipole-dipole. And this is only present when there's a big enough difference between the electronegativity of the elements involved. So CHF3, that's actually, well, carbons bonding with the hydrogen, yes, but it's also carbons bonding with the fluorines. So carbon and fluorine, okay? Because CHF3 looks like this. All right, that's how it's going to bond. Like the hydrogen is not attached to the fluorine because the fluorine is already full. OF2 looks like this. HF looks like this, and CF4 looks like this. So CF4 and CHF3 look quite similar to each other. Okay, that's a big hint on what type of bonds are present. Okay, so back to the dipole-dipole. Okay, fluorine 3.98 electronegativity, carbon 2.55. So 3.98 minus 2.55 1.43. That falls in the range of a polar covalent bond because it's greater than 0.4. So this has dipole-dipole bond because it forms dipoles between the carbons and the fluorines. Oxygen difluoride. So that one, oxygen has 3.44 and 3.98. So that one barely makes it 0.54. So that's also considered a dipole-dipole bond. So even though oxygen itself would be a non-polar molecule, since as you can see here, actually it'd still be a polar molecule because it actually has valence electrons that also express its own polarity. Point being though is that it does form a dipole-dipole because these are polar covalent bonds. HF also a dipole-dipole because hydrogen and fluorine, that is going to be what's present there because 2.2 and 3.98. Just to verify with math, 1.78 difference. And then CF4, kind of like the CHF3, okay? We're still comparing carbon and fluorine, and so it also has a dipole-dipole bond. So all of them would have dipole-dipole. Now the next one we're talking about is ionic. We're just going to skip here. Actually, not yet. We're talking about hydrogen bonds. Okay? And there are only 3 types, okay? When nitrogen's attached to oxygen nitrogen attached to hydrogen directly, oxygen attached to hydrogen directly, or fluorine attached to hydrogen directly. Of these, the only hydrogen bond present is here. As you can see here, the carbon and the hydrogen, they're the ones attached, not the hydrogen with the fluorine. So we only have one of them that has a hydrogen bond, which is HF. These are going to be the intermolecular forces present. And now, last one but not least, ionic bonds. Okay. Technically, that's not an intermolecular force, so we don't mention that one. It kind of serves as both. But do we see any metals and non-metals? No. So that one is none. None of them have that. So I'm going to actually list it here anyways. Okay. None of these, all of these here listed, all these elements here are actually non-metals, so there's none. So the key thing is that the strongest one actually would be the hydrogen fluoride, or hydrogen monofluoride, or not fluoric acid. It would be HF, hydrofluoride. I feel like I'm saying it wrong. Hydrofluoric acid. That's what. Yeah, hydrofluoric acid. That is the name of this. Would be the strongest one in terms of the intermolecular forces. So all the molecules are made of covalent bonds. However, OF2 and CF4 have polar bonds that act in opposite directions and are of equal connectivity. Hence, they are non-polar covalent bonds. That's not true. They're still polar. It's just a non-polar molecule. As a result, the strongest type of intermolecular forces in them is the Lund dispersion force. It still forms poles, so technically I wouldn't agree with that. The intermolecular force present in CHF3 is dipole-dipole interaction, which is true. HF bonds are hydrogen bonds by nature, which is also true. So this is partially correct. They are still polar bonds. It's just a non-polar molecule. But the polar bonds, yes, exactly. The polarities would still interact with each other. So, although, and in fact, even a more for example is OF2, because of the fact that it's actually going to still have lone pairs on the oxygen still, that one is definitely going to be polar. OF2 is going to be a bent shape, just like H2O. So just to keep that in mind, they will still interact. the dipole-dipole forces are still there. It's just that each side, in a sense, has its polarity. It's not kind of leaning towards one side, kind of like with the CHF3. Okay? And yes, HF, hydrofluoric acid, is going to be the strongest type because of its hydrogen bond. Okay? So with that, let's move on to the next question. So what are Bronsted acids and bases? Okay, so Bronsted acids and bases. Okay, so the key thing to understand of a Bronsted-Lowry acid is that it's able to donate a proton. Okay, donate protons. The bases, okay, accept protons. All right. Now the trick about this, you have to recognize which when it's appropriate that it can donate and when it's appropriate that it can accept. Okay. Perfect example, CH4. All right. This is neither a Bronsted-Lowry acid or a base. It's actually a neutral compound. And you're probably wondering, wait, but it has so many hydrogens attached to it. This ties in with the electronegativity aspect, okay? And also its electron number. We'll first discuss electronegativity. When you look at carbon and hydrogen, the electronegativity between them is 2.55 minus 2.20. These is 0.35, okay? And based on our limits of 0.4 and greater being polar covalent bonds, these are non-polar covalent bonds, okay? And with that being said, along with the electron number, okay, so CH4, all right, it looks like this with 8 electrons in total. If we did the math, okay, carbon, the electron number likes to have 4, and it doesn't have any lone pairs, but it's sharing 8 electrons with the surroundings. It's equal to 0. The carbon, and not just carbon, but when it comes to a lot of elements, they like to stay as close as they can to 0 for that electron number. They want to be able to match their I guess valence electrons with actually what they're working with in terms of like whether they're sharing and such. The hydrogen attached to it, okay, it'd be 1 minus, it doesn't have any by itself, and it's going to be 2 over 2 because it's sharing those two, so it's also 0, okay? Now, with that being said, there are some things that are okay with breaking that rule to get bonds, okay? Per examples are NH3 and H2O, okay? These are examples of both technically Bronsted-Lowry acids and bases. H2O is one that's confusing me. NH3 is an example of a Bronsted-Lowry base because if you draw out its Lewis structure, it has one lone pair. This is a part that is perfectly fine accepting a proton. Now, although when it accepts a proton, the nitrogen becomes +1 for its electron number, to nitrogen, that is worth it because of the not necessarily the electronegativity, although that does play a part, but more specifically the hydrogen bonds. That's why it can kind of take or get rid of hydrogens, because I guess gain it gets from getting a hydrogen bond, which is very strong, is worth the loss of losing, I guess, its neutral charge to become a positive charge. But you will never see, well, rarely, unless you really force it, you won't see NH2 by itself, NH2 minus. And in fact, it'd be NH2. Let me see here, because NH, because you gain the hydrogen, take it away. Yep, it'll be NH2 minus. Okay, you would really not see that because now it's lost a hydrogen bond and the nitrogen is at -1 for the electron number. That is like, why would it do that? It has now less of both sides. It's no longer stable and it has less hydrogen bonds. Okay, water can work as a Bronsted-Lowry acid or base for kind of a similar reason. Okay, it has 2 lone pairs. All right, so with water it can give away one of the hydrogens, go down to 0, and it's okay actually being OH minus, unlike the nitrogen, because hydroxide, it's like, you know what, I'm fine with this, strangely enough. Not really sure why, but that's what oxygen is okay with doing. But it can also use one of them and gain a proton there to become H3O and kind of almost look like NH3. And this is where oxygen will be a plus. And this one is kind of similar reason where it's like the joy of gaining a hydrogen bond cancels out the risk of, you know, of becoming a positive charge, of like losing its neutral balance. Okay, so that is what's happening there. So I guess the point of all this is to make sure that when you are seeing your molecules, make sure you're pinpointing which lone pair is okay with accepting a hydrogen. Okay, because you won't see this. Okay, this is too much. Although it has a hydrogen bond, okay, this is very unstable because now oxygen is at 2+. Okay, and it really, like at that point, it's like, yeah, I'm way too far from my neutral charge. So that's why this bond here would not serve as, you know, the Bronsted-Lowry base. And that's why you have to be really careful which lone pairs you pick. But on the flip side, you also have to be really careful about which hydrogen you're trying to give away. Like for example, in methane, those hydrogens are staying. You're not going to be able to like make carbon give away one of those. Okay, for nitrogen, for ammonia, same thing. Those hydrogens are staying. If you had NH4+, okay, which is when this gained the hydrogen, this now can give away an acid. Okay, it's to go back to ammonia. This is ammonium, that NH4+, and then NH3 is ammonia. Okay, so that is just a tricky part of Bronsted-Lowrys and bases, is that you have to be able to identify which one actually can be given away and which space actually can receive a proton. So number 18. What is the electron configuration of magnesium? So okay, so magnesium is the 12th element. Okay, so if we did the same 1s, 2s, 2p, 3s, we're going to stop there. Reason being is that 1s, we blow right past the hydrogen and helium, so we're done. And then 2s, we're past lithium and beryllium. So right now we have 1s2, 2s2, because those are checked off. And we're also gone past boron through neon, so that'd be 2p6, and then we actually stop at 3s2. So that's where we stop there. We don't touch the 3p row because we don't go into aluminum. So this will end with 3s2. And if we were to write this in shorthand notation, starting with the noble gas, it'd be neon 3s2. This would be our electron configuration of magnesium. Reason being is because our S subshell, as you recall, will be the first two columns. Okay, our P subshell would be columns 13 through 18, except for helium. Helium counts as an S orbital. Okay, so if we count it through, we have 1s1, 1s2. Then we go down to lithium, 2s1, 2s2. Then we skip over to boron, which would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 at neon, and then we have 3s1, 3s2 for magnesium. And this actually coincides with the valence electrons it has. Considering that magnesium on the second column, we know that it has 2 valence electrons, which is actually what this electron configuration is also showing, because in the most outer shell, the 3, it has 2 in the superscript. Okay? So, with that being said, this is correct, because it goes 1s2, 2s2, 2p6, 3s2. So now, with that being said, I do believe this is the perfect time to stop right there. Okay. I just want to thank you again for joining me this evening. If you have any further questions or wanted to delve more into any of the questions we've answered here, please check out the links in the description below. And with that, once again, I wish you a great night, enjoy your weekend, and thanks for joining us this evening.